Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about the famous equation E equals mc squared. And what does it have to do with what we've been talking about in this course? If you look at Wolfson's book, E equals mc squared doesn't show up anywhere in the two chapters on energy. And as you probably know, you certainly know if you've taken Physics 100, that E in this formula stands for energy. So what's the deal? Let's see if we can talk about a little bit about Einstein's famous equation, which is he is apparently in the process of discovering in this cartoon, and what it has to do with the Newtonian or classical mechanics that we are discussing in Physics 107. So, the guiding fundamental principle that underlies our discussion of energy is the so-called energy principle. And the way we talk about the energy principle is we have to first very carefully establish the ground rules. And the ground rules are we have some system. We're going to specify some physical system that we're going to be considering, and we're going to draw a dotted line around the system, and we're going to divide the world into a system and its surroundings. And then the energy principle says that we can calculate changes in the energy of the system just by looking at the work that's done on the system by the external surroundings. And Wolfson calls this quantity on the right-hand side W sub ext for the external work done by the surroundings on the system. And suppose our system, let's take a simple case, which is how Wilson starts off in chapter 6, considering a system which consists just of a single particle of mass m. Well, in that case, the energy of the system is just the energy of a single particle of mass m. We'll call that E particle. And the energy of a particle of mass m is it's purely kinetic energy, and that energy, according to chapter 6 in Wolfson, is equal to 1/2 mv squared. That's the kinetic energy of the particle. Okay. And then the energy principle says that the way you can change the kinetic energy of the particle is by doing work on it. So if you do work on the particle from the surroundings, they exert forces on the particle, they do work on the particle, and you can use this formulation here to calculate the change in the energy of the system just by knowing the amount of work that's done on it. And this is the way physics worked until the landmark year of 1905, when Albert Einstein, then a 26-year-old patent clerk working in Bern, Switzerland, said, "No, no, no, you're using the wrong expression for the kinetic energy, for the energy of a particle. The energy of a particle, according to Einstein's theory of special relativity, should be uh, the following expression. It's equal to 1 over the square root of 1 minus v over c, quantity squared, times mc squared, where c is the speed of light, and that has a known value of 3, the speed of light in a vacuum, which has a value of 3 times 10 to the 8th meters per second, a very high speed indeed. So basically, this is the view from Newtonian physics of what the energy of a system consisting of a single particle should be, and Einstein writes down a different result. And these two things, when you look at them, seem quite different from one another. So let's see if we can reconcile those differences. So it turns out that these two expressions here, 1/2 mv squared and this much more complicated looking thing, aren't quite as different as they might appear at first glance. And the way to see that is to take advantage of something known as the binomial approximation. Binomial approximation. So what is the binomial approximation? Well, the binomial approximation is a purely mathematical statement. There's no physics in this. It's a mathematical fact that if you have an expression of the form of 1 plus epsilon raised to the nth power, you can approximate that as 1 plus n times epsilon. And that approximation is a good approximation to the extent that the magnitude, the absolute value of this quantity epsilon, is small compared to 1. So, for example, if you wanted to calculate something like the square root of the number 1.001, well, you can write that as the number 1 plus 0.001 raised to the 1/2 power. And according to the binomial approximation, in that case, the quantity epsilon has a value of 0.001, and the quantity n has a value of 1/2. So according to the binomial approximation, this should be approximately equal to 1 plus 1/2 times 0.001 or 1.0005. And you should go and get out your calculator and ask your calculator what it thinks the value of the square root of 1.001 is. And you'll see that you get a number which is not exactly equal to 1.0005, but very, very close. So that just means that this is a good approximation. Okay, and this is true for any values of n and any values of epsilon. Epsilon can be either positive or negative. This is going to work as long as the magnitude of epsilon is small compared to 1. Okay, so now let's look at Einstein's expression for the energy of a particle of mass m. Einstein says that this is, I'm just going to rewrite it slightly. I'm going to write this as 1 minus v over c squared to the minus 1/2 power times mc squared. And I'm going to use, I'm going to consider cases. Suppose the quantity v over c squared is small in value compared to the number 1. Well, then you should convince yourself using the binomial approximation that in those cases, which are often going to be the case because the speed of light is a very big number, and in everyday life, the velocities that we deal with are very small compared to the speed of light. So, especially when you square v over c, you're going in everyday life, even with speeding rockets, the quantity v over c squared is going to be small compared to 1. So in all of those cases, we can approximate, according to Einstein, the energy of a particle as 1 plus 1/2 v over c squared. That's applying the binomial approximation to this part here, times mc squared. And you can just rewrite this as mc squared plus 1/2 mv squared. Aha! Well, 1/2 mv squared that arises when we make this approximation, of course, exactly matches the expression that Newton had for the energy of the particle. There still is this difference, though. Einstein's expression uh, involves this term mc squared. There's this energy that is appearing, and we call this energy the rest energy, or E sub rest. So Einstein is saying that the particle, in addition to this 1/2 mv squared term, it also has an energy equal to mc squared. But what you see is that this mc squared doesn't change typically. It's just a built-in characteristic of the particle. And as long as the particle doesn't change its mass, then mc squared is just going to be constant. When you do work on the particle, this term is going to change, but this is just going to be this constant that doesn't change. So when we go to apply the energy principle, which we write in this case as delta E particle is equal to the work done by the surroundings on the particle, uh, the fact that it has rest energy, that the particle has some constant rest energy, doesn't really affect anything. The energy principle can still be applied. So the bottom line is that as long as we deal with speeds that are small compared to the speed of light, everything that is written in chapter 6 and 7 of Wolfson is absolutely consistent to an excellent approximation with Einstein's view of things. And it's only when we get to particle speeds that begin to become comparable to the speed of light that you really have to stop using this expression 1/2 mv squared for the energy of the particle and adopt what we would refer to as the relativistically correct expression. But in Physics 107, we're going to deal exclusively with particles, objects that are moving at speeds which are small compared to the speed of light. So we won't really have to worry about relativistic effects in Physics 107. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.